What's the next lesson after this? According to your timetable.
This is not computer science.
Are you sure?
Computer science.
Computer science after lunch. It's geo. The last lesson.
Yes, sir.
Anyway. So let's look at preparation of salts. Huh? I'll just do a recap, things that everyone should now know. Now, I said, please memorize the what? The solubility what? Table. Preparation of salts. I said, please memorize the solubility table. Just to do a recap, we said all nitrates are what? What did you say? All nitrates are soluble. That's what we said. We said all group 1 salts, as long as it involves a group 1 metal, all group 1 salts are soluble. Do you agree with the teacher? We said all sulfates are soluble, except what? Without looking in your notebook. Except barium sulfate. Why are you looking in your notebook? You have forgotten. And lead what? Sulfate. You're supposed to must memorize this. It helps you to be good in this topic. What did you say again? So all carbonates are insoluble. All carbonates are insoluble. That's what he said. Insoluble. Except what? Sulfates. Huh? We are looking at this ion here. Remember, this is the sulfate ion. Huh? Remember? Carbonate ion is this one here. That's what we're talking about. All carbonates are insoluble. What's the exception? Except group 1. Group 1 carbonates, obvious. Group 1 and ammonium NH4 plus. Huh? Clear. Ammonium carbonate. All chlorides, what did you say about chlorides? All chlorides are soluble. Is that true? Chlorides from the Cl. All chlorides are soluble. All chlorides are soluble. What's the exception? What's the exception? Except what? Silver chloride and what? And lead chloride. Clear? You see things that I need to remember. Number 6, all hydroxides are insoluble. That's what he said. All hydroxides are insoluble. Except, what did we say? Except mainly group what? Group 1 and magnesium hydroxide. Was group 1 NH4 plus and magnesium. That's what we said there. Clear? Makes sense because it's partially soluble. Are we together there? That's what we said. We need to remember this. Then I said the easiest thing in chemistry is preparation of insoluble salts. Preparation of an insoluble salt. From that table there, what are the insoluble salts? Give me the insoluble salts. Barium, sulfate. Do we agree? The table? Or you disagree with the teacher? Barium sulfate, lead sulfate, silver chloride, lead chloride. Okay, you can have many other, all the hydroxides or the carbonates. Said all carbonates are insoluble. So all other carbonates that you can think of clear are insoluble, like your zinc carbonate. Clear? Is insoluble. Making sense? Now, we always get the sulfate. Where do we get the sulfate ion from? NB. We always get the sulfate ion from what? Now we want to do some important things in chemistry. Where do we, which acid always gives us the sulfate?
Acid.
Sulfuric acid. That's where we always get the sulfate. We always get the chlorides. Where do we get the chlorine from? Hydrochloric acid. I'm looking at this, how we're going to prepare this. Then the nitrates, we always get it from nitric acid. NHO3. Like this. This is very important here. So now look at this here. Why I'm saying it's important is now for me to be able to prepare, you saw in the video, for me to be able to prepare the first one there. So all this, we use a method called precipitation. That's the only method for an insoluble salt. For obtaining an insoluble salt, we use a method called precipitation. Clear? Precipitation. So what happens for the barium sulfate, we need sulfuric acid. That's what we said. Then which is in water, so that's why we write aqueous. Then we react with a compound of barium that is soluble in what? In water, clear? Which means barium chloride or barium nitrate. That making sense? So if I use barium chloride here, which is aqueous, I use a solution. So when I do that, I get what? I get my barium sulfate plus hydrochloric acid. So this is aqueous. This is a solid. Yeah. I'll put 2 there. Okay, that's fine. Clear. Now, what I didn't talk about the other day, so I'll talk about how we prepare this anyway, is there is what they call the ionic equation. So the ionic equation, look at this. Barium, if you look at your table where I said it's very important, barium is always 2 plus. Remember, it's aqueous. So the aqueous, the ions, if the ions are in water, they are always freely moving. That's why we can split them there. So we have 2 chlorines here. So it's plus 2Cl negative. Of course, it's aqueous. Yeah? I'm not writing that. Then this, we can also split because these ions are freely moving. So we have plus, it's actually 2 hydrogen plus. Hydrogen is always a plus ion here, plus 1 sulfate ion that is freely moving in water. Clear? Then always remember that if it's a solid, a liquid, or a gas, it means those ions are not freely, they are stuck to the compound. So we can't split it. So we write it as it is. Barium sulfate solid. Hope it's making some sense. Then, of course, we have 2 hydrogens in aqueous, hydrogen plus, then 2 chlorine negative. You're making sense, Brandon? That's the first stage. Then cancel things that are the same. There, that. So those are known as spectator ions. Is that making sense? They are not involved in the chemical reactions. We call them spectator ions. The chloride ion remains ClCl here. Can you see that? The spectator ion H plus, H plus. Nothing happened. So we call them spectator ions. So the full ionic equation of what we are is barium aqueous plus sulfate. Aqueous simply means it's in water, the ions are in water, to give you barium sulfate salt. That's the full ionic equation of what is happening. Are we together? That is the full ionic equation of what is happening. Besides that, they also now need you to explain how do you carry out that experiment. So what you do is you pour your acid in your beaker, your aqueous, your sulfuric acid. Okay. Then you have another solution. Okay, clear? Of what? Of your barium. It's a solution. Chloride. Okay, aqueous, AQ. So you pour that into this, clear. Then it reacts. You pour that into that, then the reaction takes place. Now we know that when the reaction takes place, we are forming barium what? Remember? Let's write it again here. We said barium chloride plus sulfuric acid to form barium sulfate, which is a solid, plus hydrochloric acid, aqueous, aqueous, aqueous. So now we have a solid that is formed. So it means a solid is formed here, clear? A solid, that's the only solid. Can you see? The rest dissolves in water. We have a solid. Each time we are reacting, we have a solid. So how do you separate a solid from liquids? You know that. From a solution, you use filtration. Do we agree? Filtration. So with your filter paper, you expect here to have your solid left behind of barium sulfate solid. Then this is just your solution. Your solution involving this, involving that, involving that. Is that clear? That's step 2. Then step 3, you wash this, you wash it with distilled water. Why do you wash with the distilled water? What do you want to remove? Impurities. To remove impurities. You want the pure salt. Purities. Clear. Impurities. I hope it's making sense. To remove what? Impurities. That's precipitation for you. Clear? Making sense? So all those salts, we do the same method. So if you wanted to prepare silver chloride, where are we getting the chlorine from? Hydrochloric acid, which is in water. Plus, give me any compound of silver. We said all nitrates are soluble, like this. So silver nitrate aqueous. Then, of course, we form silver chloride plus hydrochloric acid. This is aqueous. This is a solid, because we said it's insoluble. Clear? See why the solubility table is important? Then you can use the same method of precipitation. So insoluble salts are easy. Where it becomes tricky is separation of soluble salts. Separation of soluble salts, because we can use reacting a metal with an acid. We mainly use that for relatively reactive metals, e.g. zinc and magnesium. Clear? We can't. Group ones will explode. Group ones will explode, so we can't use that method. It will explode in acids, so we don't use that. We mainly use that for zinc and that. Clear? Then the other one is an acid with an insoluble base. Number 3, an acid with an insoluble carbonate. Then the last one is titration. Titration. This one is a nice one for the lab to show you the titration. Clear? So those are the methods that you need to know, and you need to know where to apply them and what mechanisms, so what happens. Now let's look at the first one. Reacting with an acid with a metal to prepare a salt. We said only zinc and magnesium. So if I have zinc here and I heat the zinc here, remember a zinc is a solid with hydrochloric acid, which is aqueous, to prepare zinc chloride. Plus, of course, hydrogen gas. This here is soluble, so it will be aqueous since the acid is dissolved in water. Clear? Is that making sense? Everyone? Making sense?
Yeah.
Let's look at the ionic before we look at the mechanism. So zinc. So this zinc solid here, it's a solid. No need to split it. You can't split it anyway. This is in water here, so we've got hydrogen plus ions freely moving. We've got 2 chlorine negative ions freely moving. Then this zinc is aqueous here, so I have zinc 2 plus 2Cl negative plus hydrogen gas. We can't split it. That's what we said. So what do you cancel? This only. You cancel what's the same. So it means zinc plus 2H plus to give you zinc 2 plus hydrogen gas. Clear? This is a solid here. This is aqueous. This is aqueous. The ionic. Now let's look at the chemistry. So I'm adding a powder to an acid. What should I do now? So there's something here that now you need to. For when we're preparing insoluble salts, it's not necessary. But look at this. What if the acid? What's the danger if all the acid has not reacted here? We have a mixture of the salt and what? And the acid. Is that true? Which is a contamination. We have a mixture of the salt produced and the acid, because both of them dissolve in what? In water. So that's a contamination of the salt. Is that clear? Which is difficult to what? To separate. So what do we do to make sure that, who knows, to make sure that all the acid is reacted? We use excess what? Excess zinc. Excess zinc powder. Clear? I'm adding zinc, it's reacting. I'm adding zinc, it's reacting until the zinc can no longer react. There we use warm, otherwise it dispense the word there. Warm, we can write that we use warm. This has to be warm here. Clear? But zinc is a slow, it's not a highly reactive metal. Clear? So warm hydrochloric acid. So add excess zinc. That's the idea. By adding excess zinc, doesn't mean you're taking so much zinc powder and you're doing it slowly. You are reacting with zinc. You are adding zinc, it's reacting. Adding zinc is reacting until zinc can no longer react. That's what we mean by the excess. I want to show you the technique of excess. So I add zinc, I stir that. Is remember it's in a water, whatever. Then I can see that it's reacting. I add another maybe spoon of zinc. Then I altogether until the zinc can no longer react. How do I know that the zinc can no longer react? There will be a precipitate at the bottom. Clear? We have a precipitate of excess what? Of the excess zinc. It means all the acid has been used up. The zinc can no longer react because all the acid has been reacted to form the salt, clear, of the zinc chloride. Is that making sense? Everyone? Clear?
Yes,
So we
sir.
have to use excess zinc powder so that we make sure that all the acid has been used up. The challenge now with this whole setup is that the zinc that has been produced here is in what? This zinc is in water. Do you agree? The zinc here is in water. So we want to, how do you now get the zinc from the water? Do we evaporate? Do we use crystallization?
We use pasteurization.
Okay. So what happens now is we now have this zinc solution here. So you now take the zinc solution. No, that's not the, oh, sorry about that. That's not the second, I'm lying. We haven't dealt with the excess. No one thought about it. So the second step is to remove excess what? To remove excess zinc solid, excess zinc. How do you remove excess zinc? By filtration,
Yeah.
we filter, was a solid. So we filter that. Then they filtrate the solution. So now we now have removed that. We now have this, like what you're saying. Now what's the difference between crystallization and evaporation? You need to understand it. So when I have my solution here, which is the hydrogen escapes, that's fine. So we have zinc chloride aqueous here. So we heat this by crystallization. It means we heat this until half of this solution or half of the water, clear? Half of the water has evaporated, clear? Evaporated. When that happens, this solution becomes saturated. This solution becomes saturated. Then the next thing, when that becomes, we leave it to dry. Remember, we are heating, so we leave it. We form nice crystals. We leave it. We leave the saturated solution. Or solution to dry. When it dries, it forms nice crystals of what? Of zinc. Then the last thing is we use little water, just to distilled water to remove any impurities. Little distilled water to remove any impurities. Clear? Making sense? Now we're together. Now let's look at the most important one that is always in the exams, is the formation of copper sulfate, like this. So this one here is actually, it's called the hydrated because it has water molecules. It's a solid, hydrated copper, copper sulfate. is blue, huh? Clear? It's blue in color. Blue in color. Then copper sulfate. This one is known as anhydrous. No water. Anhydrous. Copper sulfate. This one is white. Clear? Anhydrous copper sulfate. So now, anyway, let's look at how we do. I've just mentioned things that are very important. This is blue, this is white. Huh? So if you, the moment you add the water to this, form this blue solution. Huh? Now, that's not what we are interested in. For now, we're interested in how do we prepare that? How do we form that? And so let's think of copper sulfate here. We want the sulfate from sulfuric acid. So now that's where we use the insoluble base. Huh? Copper hydroxide is an insoluble base. It's insoluble. Clear? It's an insoluble black compound. Just for you to know there. There's a color, black what compound. So now we add that copper to what? To sulfuric acid. Aqueous. Then we form copper sulfate aqueous. There's what it's in water. Plus sulfate. Remember, an oxide, if you remember your acid, base, and salts, an oxide plus an acid is salt plus water. Who remembers that? Salt plus water. Yeah. Salt plus water. Looks like it's balanced. Salt plus water. This water here is a liquid. Now let's talk of the equation, the ionic, before we look at the mechanism. So copper, we can't split it, it's a solid as it is. What you can split is only the aqueous ions. So 2H plus. The more we do this, the more we get used to this. Sulfate ion, we form copper sulfate, so we can split it. And the sulfate ion. Then the water is a liquid. It's joined together, we can't split it. Clear? So spectator ion is only the sulfate. Clear? So the full ionic equation, can I write that? Like this. Are we together? In terms of the experiment, step 1, you are adding. Normally they give you these steps, or they say explain or plan an experiment. So now we are adding. So we've got your sulfuric acid. Then you add aqueous what? Excess of the source of the powder. Excess copper oxide. So that all the acid reacts. Then the next thing is filter the excess copper oxide solid. Clear? Then the next thing is now to use to do crystallization. Clear? Crystallization. So you say heat to saturation. Heat the copper sulfate solution to saturation point. Clear? To saturation point. So heat the copper sulfate solution to saturated point. Then number 4 is that leave it to dry. Number 4, leave the solution to dry. Then lastly, use little distilled water. Clear? Use little distilled water to remove impurities. Then you're done. Are we together? To remove impurities. Clear? Clear or not clear?
Yeah.
Okay. The last one now is the method of titration. So maybe just to help you so that you always remember, this is used for preparation of group 1. Preparation, and I'll explain why. Preparation of group 1 salts. Neutralization reactions. Preparation of group 1 salts. So for example here, if I have sodium hydroxide plus hydrochloric acid, I form this table salt sodium chloride plus H2O. But there's a big challenge here. Look at this here. This is aqueous. This is aqueous. This is aqueous. Then of course you've got water, which is a what? Which is a liquid here. What is the main challenge? You can tell me what is the main challenge from this experiment here. We've got 3 aqueous solutions. Huh? How are we going to separate the hydroxide from the salt? Huh? It's very difficult. Huh? Clear. Because both of them are what? Are aqueous solutions. Can you see that? So that's the challenge. So for that now, group 1, because group 1, we can't look for any insoluble. Group 1 clear. Because all group 1 are soluble. It's different from all the others. We're forming soluble compounds. Huh? I'm saying we're forming soluble from insoluble. If we're looking at the other, we're taking of soluble, preparation of soluble salts. Huh? But with the group 1 now, that's the challenge. Yeah? That we have a challenge like this. So we can only use what? Precipitation. Clear? Now I'll explain how we do precipitation now. Is that in a lab, I wish I could show you the diagram. Maybe I'll show you at the end. Yeah, maybe let me show you a 3 minutes precipitation video there. 3 minutes, a short one. Now, how we do this, everyone, the stages are important, is that I measure 25 cubic centimeters of HCl aqueous. What do I use? I use the what? What measures 25 exactly in a lab? Which instrument? A pipette. We measure exactly this. Clear? You pipette. Then of course you put it in a what? In a beaker like this. I don't write this. Maybe anyway, you can write somewhere, but I think I'll give you, especially this one here, I have to give you the correct things in the correct order. We now have this. Then because it's an acid, we add what? We add an indicator. So we use methyl orange indicator. So the moment I put few drops, so if I put few drops of methyl indicator, what solution does it turn? Turns red, because it's an acid. It turns red, clear. Then now I put the sodium hydroxide here in a burette, because a burette will allow me to do drop by drop, clear. So I put a drop, I shake it, a drop or a few drops, I shake it until the solution turns what? Orange. and I stop. Clear? The solution turns orange, I stop, I take my reading of what volume have I used of sodium hydroxide. Then I repeat the whole, now, for example, if it's maybe close to 48, I'm just saying as an example, it means now when I'm close to 40, I have to be very slow because I want the exact volume of what reacts with this. Clear? The reason why I want the exact volume is once I know the exact volume, now my third experiment, I'm simply measuring that volume. I now know the volumes that they react with, the ratios. I now know the volumes. So it means only this will be produced. Without this, all this will react. Because even I now know the actual volume, that for 25 cubic centimeters, how much volume do I need? If I now know, so the reason for doing this is so that we find the exact volume of the sodium hydroxide that should react with this. If we now know that volume now, we now do the third experiment without the burette. We are simply now adding that. Then this salt is formed. Clear? And sodium chloride in water, we can simply use evaporation. Are we together? Evaporation. Now, maybe the last thing, so I said I will show you just now. What's the last thing? If I use very high heat and I use slow heat, what's the difference in the salt that is formed? If I use very high heat, it can easily break this salt. Clear? But if I use slow heat here, I can form nice big crystals of my salt. Clear? You need to know that. Now, let me just show you quickly what we are talking about here. The experiment. Then next time we'll look at questions. Preparation of salts. Exam question, especially for your paper, practical paper. That's where you get most questions on preparations of salts. Clear? Oh, lost someone. That's all then. Okay, hold on. Let's see. Do a new share.
Base, an alkali that is, and an acid. Now the reaction I'm going to do, I don't know if you can see that, is hydrochloric acid plus sodium hydroxide. Both of those are soluble. So if we're going to make a salt which is neutral, we've got to have exactly the right amount of acid to neutralise our alkali. Now our alkali here is corrosive, so I've got to wear lab coat and goggles. And I'm now going to measure out an exact quantity of the alkali. I'm using what we call a volumetric pipette. In the exam you can just say a pipette, but we're measuring out very carefully an exact volume of the alkali. And there's a line on the pipette that tells me how much is 25. I get the liquid down to there, and I put it in a clean conical flask. And that just runs down into the conical flask. It takes a few seconds for it all to get in there. In the meantime, I've put some hydrochloric acid in my burette, and I've made sure that the burette is reading exactly 0. Underneath the burette, I've put a white tile just to make sure we can see when we've exactly neutralized our reaction. So there's our alkali in there, hydrochloric acid in the burette. We add a few drops of indicator. 1, 2, 3, 4, 5, near enough. That is phenolphthalein. It's very good. It gives a nice clear colour. Bright pink when it's alkali and colourless when it is acid. Colourless, not clear. A lot of people say clear, but it's already clear. It's a clear pink liquid and it goes to colourless in acid. Now I'm going to add a bit of acid and I swirl it around to mix it, and I keep adding the acid until it goes colourless. And hopefully that shouldn't take too long. I'm adding quite a bit at a time just to do it quickly, but I have an idea roughly of how much I'm going to need to add. And there we are, it's gone colourless. Now at this stage I read on the burette the volume of acid I have added. And it may not be possible to see that, but I've added 11.8 centimetres cubed. And I'm just going to pause the video there. Okay, now I've added done my first experiment, and it took me exactly 11.8 centimetres cubed of my acid in the burette to neutralise my alkali. So I know how much acid I need. So this time I don't need to use any indicator. My experiment is going to be exactly the same as before, but without the indicator. So first of all I measure 25 centimetres cubed of alkali, exact, using the volumetric pipette, and I get my eye down to eye level, in case I look a bit stupid squinting at the pipette. I let my 25 centimetres cubed in. So this time my burette has a different purpose. I'm simply going to add 11.8 centimetres cubed exactly. And once I've done that, we'll be left with a pure solution of sodium chloride in water. There's my balanced equation again. HCl plus NaOH gives NaCl plus H2O. Now, if I'm trying to make a salt, I don't want phenolphthalein to be in there as well, because it's just contaminating the thing I want to make, and what's more, phenolphthalein is poisonous, so we certainly don't want that in there. So this time, I've got my alkali. I'm just going to run acid in until exactly 11.8 centimetres cubed has been added. I don't need to stir it at the moment. It's important just to add the right amount. And you can't see it from there, but I've now added 11.7, 11.8. One last drop for good measure. Swirl that around, and that is a neutral solution of sodium chloride. Step 3 is we're going to evaporate off all the water. Now notice the solution is completely clear. There's no need to filter this. It's completely clear. We pour it into an evaporating basin, and the last thing we want to do now is to warm up the liquid to evaporate off the water. Okay, then step 3 of making a soluble salt from an alkali and an acid is to evaporate off the water. Quickest way to do that is simply to put it in an evaporating basin and Bunsen burner on full, boil off the water. And you can probably just about make out that that one's bubbling away. There we go. And it might take a while to do that. So here's one in the greatest tradition of Blue Peter that we made earlier. You might just be able to see some white solid in there, and those are hopefully pure crystals of sodium chloride solid. Okay, so that's how to make a salt.
Okay. Are you guys there?
Yes.
Oh, you've gone for breakfast. Okay. So now the last thing, okay, that's is just for, okay, I think it's the next lesson. Okay, it's just to look at the equation. Can you see my whiteboard?
No, sir.
No, sir.
Can't see my whiteboard. It's just to quickly look at the chemistry part of it. So, of any neutralization reaction in group 1. So we said sodium hydroxide plus hydrochloric sodium hydroxide, which is aqueous, dissolves, plus hydrochloric acid, aqueous. Then we are forming sodium chloride aqueous. Then we are forming H2O liquid. So this is sodium ion, OH ion. We always split the aqueous ions. They can freely move. Chlorine negative, giving us sodium positive, chlorine negative, plus H2O. We can't split it. It's a compound liquid. This cancels, spectator ion. This, no, that doesn't cancel, sorry, because there's no H plus here. The chlorine cancels, clear. So what we now have is H plus OH negative plus. So what I wanted to mention is that in chemistry, if you reduce any acid-base reaction and it reduces to this is a special reaction. It's a neutralization. That's the ionic equation for any neutralization reaction. For any neutralization reaction. Because they can give you in paper 1 and saying an ionic equation reduces to this. What can that tell you about the reaction? It's a neutralization reaction. Clear? Any neutralization reaction will reduce to that. If it doesn't reduce to that, it means it's not a neutralization reaction. Are we together? Making sense?
Yes, sir.
Any neutralization reaction will reduce to that. So we are done. It's time for computer science.